Way back in the early days of the internet, Google had a problem nobody had ever really faced before. I mean, they were trying to index the entire web. The question was, where in the world do you store all of that? So today we're going to dive into how Google solved this planet-sized problem by building its very own foundation, the Google File System.
Just take a second and really think about that. We're not talking about your family photos or a couple of big documents. We're talking petabytes and petabytes of data for search, for Gmail, for what would eventually become YouTube. The amount of information was just staggering. And your standard off-the-shelf storage systems, they just weren't built for it. They couldn't cut it.
See, Google's needs were completely unique. They needed a system that could handle insanely huge files. It had to run on thousands of cheap, regular commodity computers, not expensive, specialized hardware. And here's the big one. It had to treat hardware failure as a totally normal, everyday event. Their workload was also different. They were mostly reading enormous files and just tacking new data onto the end of them, not constantly going back and changing the middle.
So, what they came up with was the Google File System, or GFS for short. And honestly, the best way to wrap your head around its design, which is just ingenious, is to stop thinking about it as a computer system and start thinking of it as a massive, super efficient library. Every great library needs a great librarian, right? In GFS, that's the master server. You've got this one all-knowing server that holds all the metadata. It knows the name of every file, it knows all the little pieces that make up that file, and it knows exactly where every single one of those pieces is. But, and this is so critical, the master is just the coordinator. It never actually touches the data itself. It just tells you where to find it.
So, the data, the actual books in our library, they're stored on what GFS calls chunk servers. These are the bookshelves, and they're not fancy. We're talking hundreds, even thousands of regular computers, each with its own set of hard drives, just doing one simple job, storing whatever data they're told to.
And what are they storing on those shelves? They're storing chunks. Because the files in GFS are so enormous, they get broken down into these large, standardized, fixed-sized pieces. It's kind of like a massive encyclopedia set, you know, where every single volume is the exact same size. In GFS, each of those volumes is a chunk.
And when we say large, we are not kidding around. Each one of those standardized volumes, every single GFS chunk, is a whopping 64 megabytes.
Okay, now let this sink in. A normal file system, like the one on your laptop, probably uses blocks that are around 4 kilobytes. A GFS chunk is over 16,000 times larger. This wasn't some minor adjustment, it was a radical choice. And the payoff was huge. It dramatically cut down on the amount of location data the master had to keep track of, which meant it could store all of that info right in its own RAM for lightning-fast lookups.
Okay, so we've got our librarian, the bookshelves, and the books. How does a client, like an application, actually read or write a file? Well, the secret sauce is a core GFS principle, separating the control traffic from the data traffic.
The way you read a file is just beautiful in its simplicity. Your app asks the master, hey, where can I find the chunks for this file? The master looks it up and replies with a list of the chunk servers that have a copy. Then, and this is the key, your app completely bypasses the master and goes straight to the nearest chunk server to grab the data. The master is now totally free to go help someone else, which keeps it from ever becoming a bottleneck.
Reading is one thing, but writing's a whole different beast. If you've got multiple clients all trying to add data to the same file at the same time, how do you stop them from stepping on each other's toes and turning the file into a corrupted mess? How do you maintain order?
GFS has this really elegant solution called a chunk lease. For any given chunk of data, the master picks one of the copies and says, you're the primary. You can literally think of it like handing that server a talking stick. For a little while, only the server holding that lease, the primary, has the authority to decide the order of any changes to that chunk.
And here's where you really see that brilliant separation of data and control. First, a client pushes the new data it wants to write to all the copies of that chunk. They just hold on to it. Only after they all have the data does the client send a tiny write command to the primary, the one with the lease. The primary then just picks a serial number and tells the other copies, okay, write the data now in this specific order. This guarantees that every copy of the data is changed in the exact same sequence. It's genius. Now let's talk about one of the most incredible parts of GFS. Remember, this whole thing is built on thousands of cheap computers. And what do cheap computers do? Well, they break. All the time. Hard drives die, power supplies pop, networks get flaky. GFS wasn't just designed to tolerate failure, it was designed with the absolute expectation that things would be breaking constantly.
This one sentence, right here, This captures the entire engineering mindset behind GFS. If you start with the assumption that your components are unreliable and will fail all the time, you build a fundamentally different kind of system. You build resilience and automatic recovery right into its DNA, not as some feature you bolt on at the end.
So, how do you build a reliable system from unreliable parts? The #1 strategy is aggressive replication. You make copies. By default, every single 64 megabyte chunk isn't just stored in one place. It's copied and stored on at least 3 different chunk servers. And they're smart about it too. GFS tries to put those copies on servers in different physical racks, so even if a whole rack loses power or its network switch dies, your data is still safe.
So what happens when one of those chunk servers inevitably kicks the bucket? Well, the master notices pretty quick, because the server stops sending its regular little "I'm okay" signal, which is called a heartbeat. The master immediately checks its records, figures out which chunks just became under-replicated, and automatically tells a healthy server to make a new copy from one of the survivors. The system just heals itself. No human intervention needed.
But it's not just about servers completely dying. What about a more silent killer, like bit rot, where the data on a hard drive just quietly gets corrupted over time? GFS handles this with something called checksumming. Each big chunk is divided into smaller blocks, and every single one of those blocks gets its own unique digital fingerprint. It's checksum.
So whenever data is read, the chunk server quickly verifies this fingerprint. If it doesn't match, it knows the data is bad. It immediately tells the client, nope, try another copy. But at the same time, it reports the corruption to the master. And the master, just like with a failed server, schedules that bad copy to be deleted and replaced with a fresh one. Data corruption gets stopped dead in its tracks.
So, GFS was obviously a monumental achievement, but its laser focus on Google's specific problems meant it came with a very distinct set of trade-offs. It was absolutely brilliant for what they needed, but it was definitely not a one-size-fits-all solution for everybody.
And you can really see those trade-offs here. I mean, the design was brilliant. That simple, single master approach gave them massive throughput for huge files and made it super fault-tolerant. But the flip side of that coin is that the single master could be a bottleneck, and the total amount of file information was limited by how much RAM you could stuff in that one machine. It was perfect for giant files on cheap hardware, but that same design made it pretty bad for storing, say, millions of tiny files. GFS was a masterclass in designing for a specific problem, not for every problem.
The legacy of GFS is just immense. Its core ideas, checksums, heartbeats, replication, designing for failure, they became the blueprint for the entire big data world that came after. The open source system Hadoop, it was directly inspired by the GFS paper. So the real story is that GFS was Google's private solution to its own unique, massive data problem. But the ideas were so powerful that they escaped the lab and now pretty much power our modern digital lives. And that leaves us with a final thought. What happens when everyone has a big data problem? Google's answer from 2 decades ago is still echoing today.